the valley dried up and almost everyone left. In the 1950s, astronomers from Caltech moved in, establishing an observatory to study the radio waves emitted by a host of celestial objects. On the same site is the Owens Valley Solar Array, an experiment dedicated to listening solely to the sun. Now operated by the New Jersey Institute of Technology, NJIT, it has recently undergone a major upgrade to double the number of antennas. The world-leading facility has been renamed the Expanded Owens Valley Solar Array, EOVSA, and astronomers are using it to study our nearest star in unprecedented detail. Its souped-up dishes came online in April 2017, and just 5 months later, a huge active region rolled around the western limb of the Sun. Between the 6th of September and the 10th of September, it produced the most powerful solar flares seen during cycle 24. EOVSA was watching, as were a fleet of solar observatories in space, including NASA's SDO. Ferocious flares. A flare is a huge, sudden release of solar energy, and the first person to observe one was Richard Carrington in 1859. During a flare, the sun gets rapidly brighter in a small, localized region. Energy is swiftly emitted across all parts of the electromagnetic spectrum, from radio waves right through to gamma rays. The Earth's atmosphere prevents some of this radiation reaching the ground, so we need both ground facilities, like EOVSA, and space-based telescopes, such as SDO, to study the full range of energy released by flares. In 10 minutes, a flare can release 10 million times more energy than a volcanic eruption, and 1,000 times more energy than the most devastating earthquakes. Some of the September 2017 flares exploded with the might of 1 billion hydrogen bombs. If we could somehow harness their power at source, we'd have enough energy to sustain the human race at our current consumption rate for 10,000 years. Yet even the fiercest take up less than 1% of the entire solar disk. Flares are ranked by their power, starting with the feeblest A-class, rising up through B, C, and M to the most ferocious X-class flares. Each class is 10 times more powerful than the last, meaning that an X-class flare is 100,000 times more potent than an A-class event. Each category is split into 10 smaller divisions, except for the X category, which has no upper limit. The 4-day flurry in September 2017 released 27 M-class and 4 X-class flares. Solar flares are often linked to active regions, and their number swells and subsides in a similar way to the sunspot cycle. Dozens of flares can detonate every day around solar maximum, but the sun can go weeks without a single flare at solar minimum. Astronomers have known since the 1960s that the peak of solar flare activity occurs a few years after the sunspot maximum, but they still do not know why. Nor do we understand why major flare events often unfold when the sun is otherwise very quiet. The September 2017 flares were the most powerful since 2006, but exploded towards the end of the unusually weak cycle 24. The immense solar flare witnessed by Carrington in 1859, still one of the largest on record, erupted during another lackluster cycle for sunspots. The solar atmosphere. What we do know is that these explosive events have their roots in the sun's atmosphere, which consists of 3 layers: the photosphere, the chromosphere, and the corona. The chromosphere is a thin region that extends a few thousand kilometers above the photosphere. Seen as a deep red rim around the sun during a total solar eclipse, it is here that helium was first discovered on the sun using early spectroscopy. Its reddish hue is due to the light emitted when electrons in a hydrogen atom drop down from the 3rd energy level to the 2nd. Astronomers call